Hi everyone. Welcome to the week 9 live section of this course, which is quantum transport. I'm Gitanjali. I'm a PhD scholar from IIT Delhi and the TA for this course. In the last week, we have covered what are the different charge stability diagram for different type of quantum dot system. Am I not audible? Hello. Can you please join again and check whether the voice is okay for you? Hello. Is it okay now? Can you hear my voice? I think the screen is visible, but let me- uh, screen is visible. And what about the audio? Can you hear my voice? Okay. Okay. In the last week, we have covered what are the different charge stability diagram for different quantum dot system. We have covered in detail and we have covered what are the different points of this charge stability diagram where we can see the Coulomb blockade oscillation and where we can't see the Coulomb blockade oscillation. For this week, we will cover the charge transport in superconductor and what are the different properties if we combine superconductor with a superconductor or superconductor with another material. So uh, besides the weekly content of week 9, I will cover few of the problems which is related to the concept of week 9. Also, towards the end of this live session, what I will do, I will try to cover few of the concept from week 10 also because I saw there are few questions from week 10. So I will not cover in detail. So I will just cover those part that will uh, helpful and that will be useful for solving the assignment. I will try to cover in brief so that it can help you to solve the assignment. So let's start with week 9. Before going into the details of the transport in superconductor, so we have to see the what is the BCS theory of superconductivity. So it basically tells about how the superconducting states are formed, how the Cooper pairs are formed in a critical temperature under the application of any external field or any other parameter. So if you recall the BCS theory, so in brief, what this theory says is that uh, only for a low temperature, only those electrons which are close to the Fermi energy. Let me take a different color. So only those, so no, it's not like all the electrons will form the superconducting states. So by superconducting states, we mean the Cooper pair. So Cooper pair means there are two electrons which has opposite spin as well as opposite momentum. They have opposite spin and opposite momentum. And these Cooper pairs are formed only around the Fermi energy, EF, and only those electron will. Okay, is it okay now? Okay, I will try to write in a big font. Okay, so what I was telling, if you consider this as the Fermi surface, then only those electrons that are in a range of h cot omega d, either plus or either minus. Only those electrons, they will only participate in the Cooper pair formation, and they will form the superconducting states. And these states are formed by phonon mediated interaction. So so they have two electrons. So what these electrons will do? One electron, when they pass through the lattice, they will deform the lattice, and by lattice deformation, we mean the phonons. So it will excite a phonon in the lattice, and the other electron can interact this phonon. And because of this phonon-phonon exchange between these two electron, and they will form the Cooper pair, provided that the interaction is attractive. And for the interaction to be attractive, what the condition we need is that the energy of individual electronic state, uh, this should be it should be greater than the repulsive Coulomb interaction. So only under this condition, this Cooper pair formation is possible. So this is one of the condition to form a Cooper pair, and one of the uh, main conclusion of BCS theory. Now, if you look at the ground state of this superconductor, so this ground state, because they have two electrons, so the ground state is nothing but this is formed by linear combination of the states of these two electrons. And the energy of this ground state of the superconductor, it is normally lower than the energy of the normal state energy. So they are much lower in energy as compared to the normal state energy. So this is another key conclusion that the BCS theory says. And the third one is that, so one of the main, also one of the key information that we can get it from this ground state is that because these two electrons they combine through opposite spin as well as opposite momentum. So that means that if spin plus up and spin minus up, if it combines, then it will give a spin zero. And this spin zero, it is characteristics of a boson-like particle. So that means initially we have fermions. Now in the superconducting state, that is the Cooper pair, they are basically behave like a boson. So instead of, if you recall the fermions, which we call that fermions mean the particle which is plus sorry integral multiple of half speed, or you can write it as n by 2 speed, and they follow the Fermi-Dirac statistics. So Fermi-Dirac statistics, we have already seen how the energy states are filled as a function of energy or as a function of temperature. Now for the Cooper base, they have zero spin, that is integer multiple of 1. Then because of that, they behave like a boson, and they will follow the Bose-Einstein statistics. Okay. So this is one of the key information that you can guess from the Cooper. Now the third thing that we have is that this superconducting state, they exist only below a temperature region, and the transition point below which we can see the superconducting state is the critical temperature. So that means if T is less than Tc, then we'll see a superconducting state, and if T is greater than Tc, then we'll see the normal state. Okay, but and this why we are getting the normal state is that for T greater than Tc, the binding energy that binds the Cooper pairs, they basically the energy is much less than the thermal energy. So the kBT for the thermal energy, it is much greater than the binding energy of this copper pair. So that is why we won't see any superconducting state for temperature greater than the critical temperature. But below the critical temperature, we can see the superconducting states. And if you want to quantify the binding energy of the superconducting state, so we say that the binding energy of superconducting state, it is 2 delta. Delta is the superconducting gap. Okay. And this 2 delta, it is roughly of the order of value 3.5 kb AC. It is roughly have the value of 3.5 kbts. Okay, so I will try to slow down. Let me know up to now everything is understandable, right? If not, I will try to cover it again. Okay. So this is about the superconducting state, how they are formed and where they are formed. So they are formed around the Fermi energy, which is a gap of h but omega d around this Fermi surface. And the binding energy of the superconducting state is 2 delta. Remember, delta is the superconducting gap. So this is the definition, superconducting gap. Okay. So next, what we will see that what will happen when we apply magnetic field. So this is the application of, we'll see the application part. So now we know what is superconducting state, how they are formed and where they are formed and what is their binding energy. Now let us see what will happen if we put a superconducting material in a external magnetic field, and what will happen when we increase the magnetic field, whether the superconducting state survive, or whether we'll see a other behavior of these superconducting states. So for that, if you this is explained through the Meissner effect. Okay. So what is Meissner effect? It is like if you put a superconductor inside a external magnetic field, then the field inside the superconductor is non-zero. So this external magnetic field, they won't be able to penetrate this superconducting material. They will wrap around this superconductor. So this is what we call the Meissner effect. So why they do so? It is like if you put this superconducting material inside a magnetic field, so this magnetic field will introduce a non-zero energy. So they will try to increase the energy of this superconducting state. So to minimize that, so if so whatever happens in nature, they will try to minimize the opposition that the other parameter is doing. So here, what the external magnetic field is trying to increase the uh, ground state energy of the superconducting state. So to minimize that, what the superconducting material will do, they will induce a surface current at the surface. So this surface current, if you recall, the current will produce the magnetic field. So this is uh, uh, one of the what I say. So if you look at the Maxwell's equation, so if you look at the fourth equation, so it says whenever we have a charge, or whenever we have a moving charge, we'll see a magnetic field. So if you recall, this is called a base mu naught J. So if there is a J, if there is a current, so there will be magnetic field, which is circling around this surface current. So that means this surface current will create a induced magnetic field, and this induced magnetic field will try to cancel, they will cancel the external magnetic field. So what will happen, because of this cancellation, there won't be any penetration of magnetic field inside this semiconductor. So this is the Meissner effect. So because of this, we have seen that the B inside this um, superconductor, it is 0. So that means B, which is mu naught H plus M, it should be 0. So the magnetic field intensity. So this is the magnetic field intensity, and this is, we call it as a magnetic field. So the magnetic field intensity is negative of magnetization. So this is one of the key property of diamagnetic material. So that means the superconducting material will behave like a diamagnet if you put it inside a external magnetic field. HFM. Where did I write HFM? Okay. So H is the magnetic field intensity. So B is, I think you are talking about this one, right? Mu naught H plus M. There is no F here. I can see. So this is the plus sign. Okay. So H is, so if you look at the physical significance, so H is like the response of a material to a external magnetic field. So if you put a material in a magnetic field, so they will try to respond, they will try to oppose, or they will try to increase, or they will try to decrease the magnetic field inside the material. And because of this, we have different types of material, magnetic material like diamagnetism, paramagnetism, and ferromagnetism. So H is, this we call it as a magnetic field intensity. This is the term for H, and the physical significance is like this is the response of uh, response of a material to an external magnetic field. External magnetic field, which we call as a B. Okay, and M is like the magnetization. Okay, so magnetization means if you put a magnetic material for a normal metal, so uh, there will be dipoles that will arrange either opposite to the application of magnetic field or in the parallel direction. Okay, so this is about the magnetization, and for diamagnetic material, this H perfectly cancels the magnetization. So that is why the magnetic field inside is completely 0. So is it fine now? So after that, let us see what will happen when we what cancels the magnetic field inside this. Whether this, if you see this semiconductor, then this, in this part, the H is minus N. So that is why B inside, if you calculate the magnetic field inside, it is 0. Because whatever magnetization is producing, it is completely cancelling the magnetic field intensity. Okay. So they cancel. So that is why inside the material, the B is 0. So what will happen when we change the magnetic field, or let's say change B, whichever is okay. So the response is same. So now when we change the applied magnetic field, that so what will happen? So there is a limit beyond which the superconducting material will behave like a normal state. So the superconducting state will break down at this limit. Okay, so that point we call it as a critical magnetic field. So critical magnetic field is like the maximum strength of this magnetic field that we can apply, or we can put the superconductor inside this maximum magnetic field, but we'll still get the superconducting state. But if we uh, apply magnetic field which is greater than this critical field, then what will happen? There won't be any superconducting state, so there won't be any cancellation. So this magnetic field will the B inside this metal will be non-zero. So that means if H or B, whichever is applicable, H is greater than SC, then we'll see a normal state. So by normal state, we mean if we put this material, then the B inside this material is non-zero. But if H is less than Sc, then we'll see a superconducting state. So let me write the superconducting state as Ss and normal state is Ns. Okay. So for this superconducting state, if we put it, then the magnetic field won't be able to penetrate. It will curve around this superconducting state. Okay. And the relation, if you recall, you must seen a graph. For different, this critical magnetic field also depends on the temperature. So it's not like it is constant value for different temperature. If you change the temperature, then the critical magnetic field, it will also change. And the relation is somewhat like this. So for TC, because it is already in the critical temperature, we don't need any magnetic field. But if you change the temperature, let's say if you decrease the temperature, then the critical magnetic field, or let's say this is SC, it will increase. If you decrease the temperature, then the critical magnetic field will increase. And the relation is SC HC at temperature. Let's say you want to calculate at arbitrary temperature T. Then for that, you need to know what is the critical field at 0 Kelvin. 1 minus T by Tc whole square. So this is what I haven't drawn in this diagram. So that means this magnetic field, the critical magnetic field, it is highest when temperature is 0 K. That is this point here. For temperature 0 K, we have a maximum critical field. But for temperature T equal to Tc, this point here, the critical field is 0. Okay. So this is about what will happen when we increase the magnetic field and what is the Meissner effect. Now, as I said, the magnetic field inside this superconductor, it is 0. But it's not like it is not completely 0 at the surface, because the surface, to give a brief reason, at the surface, they should follow the Maxwell's equation. So it doesn't go to 0 completely at the surface. To follow the Maxwell's equation, what they will do, it will drop exponentially from the surface to the bulk. So this is at TC, what happens? So if you recall, at TC, at the critical temperature, the resistivity graph. At TC, the resistivity of superconductor, it drops to 0. So it behaves like a superconductor. So this is the transition point. So above TC, there will be normal state. Below TC, there will be superconducting state. So it acts like a boundary. Okay. And resistivity at this temperature is completely 0. So that is why this material will behave like a superconductor. So we'll see current with 0 resistance. Okay. So I hope it's clear. Okay. So, as I said before, it's not like the magnetic field is completely zero at the surface. So, it drops exponentially from the surface to the bulb. So, this is what we call the London penetration day. Uh, so, the field is completely zero inside. It is no doubt it is completely zero. But at the surface, if you look at the surface, there is still some amount of magnetic field because of this boundary condition of Maxwell's. Okay, and uh, there is a relation which is already given in the lecture, which is m by mu naught ns e square. M, it is the effective mass of superconductive electrons, which is the Cooper pairs. Mu naught, this is permittivity, free space, uh, sorry, permeability. Ns is the charge density of superconductor, E is the charge of this Cooper pair. Okay. So this is about some of the information about superconductor and what are its distinct properties. Now let us see what are the different transport properties of superconductor. What will happen if you combine a superconductor with a material under different bias condition? Mu naught, it is the free space permeability. And if you look at the value, it is 4 pi into 10 to the minus 7. Okay. So next, let us see what are the different uh, transport properties when we combine superconductor with a material or superconductor with a superconductor. So what will happen? Let us see a junction between a normal metal, Nm metal. They are tunnel coupled through a thin insulator layer, and there is a superconducting state. And we are applying a voltage V. So if you look at the energy band diagram, metal and the superconducting states. So for metal, for the low temperature regime, all the states up to Fermi level, they are occupied. Up to Fermi level, they are occupied. Okay. And this is, let's say this is the Fermi level. And please remember that whenever the states are in equilibrium, they have same Fermi energy level. So if you apply a bias, then the Fermi energy level will differ. But if they are in equilibrium, then we have the same Fermi level. Okay. Uh, okay, this is for the metal where electrons are filled up to the Fermi energy. And if you look at the superconducting states, this superconducting state has a superconducting band gap because of the formation of Cooper pair. And the difference is 2 delta. So that means if you try to move one electron from the metal side to the superconducting side, because here the electron is a single particle state, and the energy of the and if you look at the Cooper pair inside this region, there is no single particle state for single electron to occupy. Only the state of this Cooper pair, which is two electron states, only this electron is allowed to move from metal to semiconductor. So that means if you try to move one electron from metal side to the superconducting side, so it's not possible. Ideally, it's not possible because of this superconducting band gap. But ideally, this is the ideal case. And this is what we see often. But what happens experimentally is that even though for this situation, even though we apply a low bias, there is a tunneling of electron from the metal side to the superconducting side. This is what we see experimentally. Theoretically, we say that the transport is not possible, but experimentally, it has been seen that for the low bias case, there is a movement of electron from the metal side to the superconducting state. And this is because of the Andreev reflection. Remember that this is only for the low bias case. For high bias case, it's possible for the electron to move, because if you apply more bias, then you will be able to move these states up and down. So for that state, it's possible to see the electron movement. But for a low bias, if the Fermi levels are they are nearly same, and for that case, ideally, it's not possible for the electron to move from metal to superconducting side. But experimentally, it has been observed that it's possible for electron to move from metal side to the superconducting side. And this is because of the Andreev reflection. So what is Andreev reflection? In brief, let me show you schematically. So what will happen for the low bias case? Let's say this is the metal side and this is the superconducting side. So what will happen? There is an electron that tries to move to the superconducting state to see the transport. But because this is a single particle state, because of that, it's not allowed to go to the superconducting side. But you can see that inside this superconducting gap, the Cooper pairs are allowed to move. They are allowed to, if there is a Cooper pair, that is a two electron state. If we have a two electron state that is moving from the metal side to the superconducting side, then it's possible to see the transport. And this is what happens in the Andreev reflection. So Andreev reflection, what happens? These electrons, if there is a electron on the metals at the Fermi energy, and remember that for the Cooper pair, these two electrons should have opposite spin and opposite momentum. The P should be opposite and the spin should be opposite. Only those electrons, they will combine. So they will combine, they will form a Cooper pair and they will go to this superconducting side. And because of this, what happens? Because there is one electron that has been taken away from this metal. So to neutralize the charge, so one hole from the metal side will be reflected. So this is what we call the Andreev reflection, that uh, even under the low bias condition, we see a conductance because of this combining of electrons of opposite spin at the Fermi surface, and to neutralize the to equate the charge, the one hole will be reflected back on the metals. Okay, so this is all about the Andreev reflection. So let me know whether this concept is clear. After that, we'll move to the high bias condition. Up to now, everything is the concept clear? Spin and momentum. Uh, uh, okay. It's like for spin, these electrons, if you look at the electron only, not the Cooper pair, for electron, they are fermions. And by fermions, we mean that they have half integer spin or some integral multiple of half integer spin. It can be half, it can be 3 by 2, or it can be 5 by 2. But for electron, it is either plus half or it can be minus half for electrons. So for under reflection, what will happen? The electron that is already there in the that is already trying to move to the superconducting side, they will pick up one electron which is opposite spin. Let's say this electron has plus half. So then this electron should have minus half to form the Cooper pair. And momentum, it doesn't have any particular value. So it should have opposite moment. But okay, so let us move to the transport properties of different type of junction. So by transport, if you recall, we are basically see what is the tunneling rate. And this tunneling rate, it is related to the transmission coefficient. Let's say I just write down. So it is related to T12, which is the transmission coefficient. And it is also related to the density of states of source and drain. If you recall, there was a formula given for this. Just look at it. So I'm just now telling what is the relation. So this tunneling rate depends on both transmission coefficient and the density of states. And also, if you want to calculate the current, then we have to multiply the charge with the tunneling rate. So if you look at the typical IV characteristics, so I have already plotted what is the typical IV characteristics of different type of junction. So this is for the case where we have normal metal to metal junction. So normal metal to metal junction under low bias, if you recall, for low bias case, if we recall one of the lecture, we can, this density of states are independent of energy because they are populated around the Fermi energy for the low bias. So that is why we say these are independent of energy. This is also independent of energy. And by taking this, we have seen that for low bias case, they follow the Ohm's law. That is I is directly proportional to B or J is directly proportional to. So this is the IV characteristics. So let us look at the three different reasons. One is the zero bias case, the reason here. For zero bias case, if you look at the uh, schematic, so there is a possibility of electron to move from left to right, and there is a possibility of electron to move from right to left. And because of that, the net current will be zero. So this is for the zero bias case. Now, when we apply a positive bias, let us say we apply positive bias to the right side and negative bias to the left side. So that means if you apply a positive bias, then the energy will go down. So that is why this is uh, figured lower than this state because we apply a positive bias. So because of that, we can see that there are available state around this region where the electron from this left side to right side can turn it. Okay, so when we apply a positive bias, then it's possible for electron to tunnel from left to right. And if we increase the voltage, then the number of available state will increase and the current will also increase. So that is why it show a linear plot. And the same concept is for reverse bias case. The reverse bias, we apply uh, positive voltage to the left side and negative voltage to the right side. So that is why this is a bit lower than the right one. We apply a negative bias here. So that means here uh, you can see there are available states here where electron can tunnel from the right to left. And when we increase the voltage, the current will increase. So this is the response of normal metal to metal junction. Now let us see what will happen if we replace one of the metal by a superconductor, which is the case here. So for superconducting state, if you look at the zero bias case, this we have already seen also. Uh, for the zero bias case, let me take a different color. So for the zero bias case, if you look at this one, this is the energy diagram, and you can see that there is a superconducting gap, and because of the superconducting gap, when you move from the normal metal side to the superconducting side, because in normal metal electrons are in single in the particle state where single electron is allowed to occupy, but in the right side we have superconductor where there is a superconducting gap, so there is no single particle state inside this superconducting gap, and only the Cooper paired states are there inside this superconducting gap. So that is why the when you move from, if you apply, if you try to move an electron from metal to superconductor, then it won't be possible to move. So that is why uh, electron can't move from the metal side to the superconductors. And now if you look at the opposite, like if you move from superconductor to the metal side, then in the superconductor part, we have a Cooper pair, which is two electron state. And in the metal side, we have single electron state. So that is why, because of this mismatch in energy, this Cooper pair won't be able to pass through this junction. So that is why any movement is not allowed. So the current is completely zero. Okay, so this is what that has been schematically drawn here. This is for the zero bias case. Now let us see we apply a voltage. Okay, so when we apply a voltage, let us say we apply a positive voltage to the metal side and positive voltage to the superconducting side because the energy are lower, and the voltage for the metal side is relatively in the negative direction. So for this part, what will happen if somehow the voltage, if the applied voltage is such that this energy level, the top of this energy level, they are in parallel with the single particle state of superconductor. So these are single particle states, right? If the energy is such that they are in parallel. Okay, so for that state, what will happen? The electron will now can move to the other side because they are there are single particles said in the superconductor side, and the voltage that is required for this is delta by E. Okay, because this is delta, right? Let me plot it here. So we have a state like this. So this is delta, right? So if you move by delta, if you apply a voltage which is value delta by E, then it's possible to see the current, which this has been drawn here. So current is 0 up to delta by E, and above delta by E, the current will increase. Similarly, we can see the same situation for the opposite case. For the opposite case also, we apply positive voltage to the metal side and negative voltage to the superconducting side. And if you apply a voltage of delta by E, then it's possible to see the current. But below delta by E, the current is completely zero because of the superconducting gap. Okay, so this is the IV characteristics of insulator to, metal to superconductor junction. So is this plots clear to you? Do you have any doubt in any parts? Otherwise, we'll move to the next part where we replace both metal by superconductor. Okay, if it is clear, then let's move to the superconductor side. So for superconductor, the IV characteristics, it's somewhat similar to what we have seen here, but here this gap, if you look at here, for the metal to superconductor, the gap is 2 delta by E, but here it is 4 delta by E. So reason is that we have superconductor on both sides. So let us see in details. For the zero bias case, no voltage is applied. So that means here we can see that even though we don't apply any bias, here we have Cooper pairs that are aligned at the same level. So that means the Cooper pair can tunnel to the right side, and from right side it can tunnel to the left side. But instead of a zero current, for the superconductor state, if you recall the metal case, whenever we have a case that it can tunnel to both left and both right, then we say that the total current is zero. But it's not the same case for the superconductor. For superconductor, if there is a possibility of Cooper pair to tunnel to both left and right side, then we'll see a peak in the current. Even under low bias condition, you can see that we are seeing a high value of current. So we'll see in the details why we are getting this. And it is related to the phase of this superconductor, of the Cooper pairs. Okay. So even under the zero bias case, we'll see a current. Now what will happen when we apply a voltage? Now instead of because we have a superconductor on both sides, the voltage, and it also has a energy gap of 2 delta. So that means if you want to level this energy level to this one, we need to lower this right side by 2 delta. Not delta, it should be 2 delta. So that is why the minimum voltage that is required for tunneling is, it should be greater than 2 delta by E. So this what you have seen here. So if you apply a voltage, then it is 0 for up to the point 2 delta by E, and for 2 delta by the value increases. This is for the forward bias, and for also for the reverse bias also. If you want to level this from left side to the energy level of this side, the left side should be moved by 2 delta. So that is why up to 2 delta the current is 0, but above 2 delta the current is high. Okay. So that means the gap, the voltage range within which the current is 0 in both the direction is 4 delta by E. Previously we have 2 delta, now we have 4 delta by E. So is this part clear? Now we'll see some of the unique effect of this tunneling in superconductor SIS junction. Like this supercurrent, we'll see this, why this happens. Okay. I will not go in details of the mathematics because it's already well explained in the lecture. So I will just try to cover what are the key points of different effect. This 4 delta by E question has been asked in week only. Do you mean it has been asked in the assignment or what? So, but keep in mind that I am talking about the whole range, not half of the range. Okay. Uh, okay. Do you have any doubt in this? Otherwise, let's move to our next part. Okay. So now let us see why there is a super current for the zero bias case and what are the other different interesting properties. So if you we have seen the DC Josephson effect. So by this we mean that for this SIS junction, even though we don't apply any external magnetic field or any external bias, still we see a DC current. So this is what we call as a DC Josephson effect. Next, we have seen the AC Josephson effect. So for DC, V is 0. For AC Josephson effect, what we see that if you apply a DC voltage, let's say BT is V0, it's a constant DC voltage. If you apply a DC voltage, for that case, we'll see that there is a current oscillation across the junction when you apply a DC voltage. If you apply a DC voltage, we see AC current. So this is what we call a AC Josephson effect. Next, what we have seen, I will go in the details. I'm just trying to cover what the effects roughly tells. So for next, we have inverse AC Josephson effect. So for this, instead of a constant DC voltage, we have a AC voltage also. So we have also a RF voltage, which is added to the DC voltage. For this part, what we see when we apply this time varying voltage, we see DC current. This is the inverse AC Josephson effect. In the last part, we have squid, that is superconducting quantum interference device. So this is like a magnetic analog of AB effect that we have seen earlier. So if we apply a DC magnetic field to a superconducting loop, then what we say that we'll see a interference effect. Okay. So these are the effects in brief, what it says. Let us see in the details. So if we have any doubt in the mathematical details, please let me know. But for now, because the mathematical details is completely, and I think it is well understood from the lecture. So to save time, let me just not go in detail through the mathematics part. I will just tell you what are the different unique effect that we'll see. So for the DC Josephson effect, that means we don't apply any magnetic field or we don't apply any bias. But even for that case, we'll see a current, and which we have seen here, supercurrent branch. Let us see why we are seeing this supercurrent branch. So to understand that, so we have a superconductor tunnel coupled through insulator, then there is a superconductor. So we can use the quantum mechanics formulation. So for the left side, let's say we can represent it through this wave function psi1, and for this part, we can represent it to psi 2. And by using the Schrodinger equation and all, we see that we can calculate the current density. J is J0 sine delta. So here we can even though, so this is all, this we have derived after using all the time varying Schrodinger equation and after equating the density of, sorry, the charge rate, the charge momentum rate, rho 1 and rho 2. After all that, we see that the current density, we can write it as J0 sine delta. So delta here, it is the phase difference between the, if you recall, delta, the general relation of delta T is delta 0 plus Q by H cut Vt dt. And for a constant voltage, you can write it as delta T is, or let's say for a zero voltage, because we are now in a zero voltage, delta T is delta 0. And delta 0 is nothing but we write it as delta, and it's the phase difference between the copper plates. So after all this, we see that the current is expressed as this. And this is the reason behind the super current branch that we have seen earlier under the zero bias condition. So we'll see this super current depending on delta. Delta is the phase difference in the absence of voltage or any electric or magnetic effect. In the next part, this is the DC Josephson effect. Now let us see what will happen if we apply a constant voltage. That is Vt is not 0, but it's a constant value which is V0. So we apply a DC voltage, and this we call AC Josephson effect. So for this part, if you remember delta T, which is the phase, this we can write it as delta 0 plus Q by H cut Vt dt. Remember that Q here is the charge of the copper pair, which is 2e, not e. So Q is 2e. And delta 0 is the initial phase. So in this equation, if you apply Vt is V0, because we are applying a constant voltage, then we can write delta T is delta 0 plus Q by H cut V0 T. So that means the phase difference, it's a function of the applied, it's proportional to the applied voltage. Also, it varies linearly with time. And from this phase, we can calculate the current density, which is given by J0 sine delta 0 plus 2e Vt by H cut. Okay. So this is the AC current we get if you apply a DC bias voltage. And the term here, it is like a term similar to a term of omega t. So that means we can say that this part it is equal to omega. Omega is 2e by h cut. And omega, if you know, this is angular frequency. And if you relate to frequency, we have 2 pi f. And h cut is h by 2 pi. So 2 pi by h, 2e v by 2e v. 2 pi will cancel. So that means we can calculate the frequency as 2e v by h. So if you are given a voltage, you can calculate what is the frequency of the uh, source that will be radiated out. So this effect is it's basically used to design an antenna which can radiate. So you can see here 2e by h. It's a relatively high value because h is very small. It's in the order of 10 to the minus 34. So that is why this value is very large. So even though if you apply a small voltage, then it's possible to see high frequency. So that means you can use it as a antenna where if you want to design it as a source or any other source, megahertz source, then by applying a small voltage, then it's possible to see the high frequency radiation. Okay. So this is about the SE Josephson effect. Now let us see what is the inverse one. The inverse SE Josephson effect. So for this part, we have a RF voltage in addition to the DC voltage. You can see here from starting from DC to inverse AC, we are gradually changing the voltage from 0 to a constant value. Now we are adding the time varying part. Okay. So for this one, we have the condition that V0 should be much greater than mu. This is the DC voltage and this part is the AC voltage. So for this part, now if you calculate the phase, this is delta 0 plus Q by H cut. V is V0 plus nu cos omega t dt. So this will give delta 0 Q by H cut V0 t plus Q by H cut nu by omega sin omega t. And after doing some approximation, that is this term is very small, we find that the current we can write it as J is, now it is J0 sin delta 0 plus QV0 t by H cut plus Q mu by H cut omega sin omega t cos the same part here. So it so for this expression, the one of the conclusion that we get is that the current is only non-zero when omega is QV0 by H. So that means to see a non-zero current or to see the transport, we need to apply a voltage V0, which is N H cut omega by Q. Or we can write it as V0 is N pi 0 omega by 2 pi. Pi 0 is H by the flux quantum. Okay. So for this one only, this will show a non-zero current. And in the IV characteristics, we'll see peaks in the current whenever this voltage condition is satisfied. So if you recall, we see a peak in the current like this for the IV. Okay. So now we'll see the last part, which is squid. Squid, it is like a AB effect. So we flow the charge carrier through different parts. So if you recall in the AB effect, we have a configuration like this. And we see that when you apply a current through it, depending on the phase here, they will interfere. So it can go, the current can go this way or it can go this way. And because of the applied magnetic field, it will have a phase at this end. Also, it will have a phase at this end. And depending on the phase difference, they will interfere and we'll see a quantum interference effect, which is similar to Young's double slit experiment. Okay. So if you look at for this path, half of this path, the delta A here is delta A is delta 0 E by h cut phi. And for the B path, it is delta B. The phase accumulated is delta 0 plus E by h cut. Sorry, not plus, it's minus. Because if you recall the magnetic flux, the vector potential and the path we are following, they are in opposite direction. We have seen a minus now. This we have seen in the earlier lecture. And now if you calculate the phase, if you calculate the current can be the superposition of this two path, which is sine delta 0 E by h cut phi plus sine phi 0 minus E by h cut phi. So this you can simplify it like this is sine A plus B and sine N minus B, which is 2 sine is positive. So we'll get I0 is sine delta 0 cos E by h cut phi. So that means we see a double slit like of experiment where the current, this will be maximum because these two are constant, right? These two are constant. Only this term is varying depending on the flux. So to have a maximum current, that means this should have a maximum value. And cos of something is maximum when it is integral multiple of phi. So that means E phi by h cut, it should be equal to some integral multiple of pi. So phi should be n pi h cut by E. So to see the maximum current, we have to have the flux it should satisfy this condition. And if you want to calculate the periodicity of this double slit kind of, so it shows a current like this, right? It will show like this. So the periodicity here is h by 2. I think we have covered all the concept that is related to week 9. Now let us see few of the questions. We'll start solving few questions first. Then towards the last 15 minutes, I will try to cover only the concept that will be helpful to solve the assignment problem. Okay. So in question 1, let me read out. So according to the BC's theory of superconductivity, which of these following statements are true? Option A, superconducting states are favorable when energy difference between the electronic states involved in pairing is less than the phonon energy. Option B, the ground state of a superconductor is higher in energy than the normal state. Option C, in superconducting states, the attractive interaction dominates the repulsive Coulomb interaction. And option D, there is an energy gap for individual particle excitation, which decreases from about 3.5 kBTC at 0 Kelvin to 0 at T equal to Tc. So we need to identify the statements which are true according to the BCS theory. Can you let me know the answer? Okay. So according to the BCS theory, let us see option A. Superconducting states are favorable when energy difference between the electronic states involved in pairing is less than the phonon energy. This is true according to the BCS theory, because only then, if the energy difference is lesser than the phonon energy, then they will combine, they will form a Cooper pair. So if you recall, I have drawn one diagram, Fermi surface, and only those electron which is as a distance h cut omega d from the within the range of this Fermi surface, they will participate. That means this is, if you roughly say this is half, then this is h cut omega d by 2. This is also h cut omega d by 2 with respect to the Fermi energy. That is, it may be this is plus and this is minus. So this state combined, they form Cooper pairs. So that is why the individual electronic state should have energy less than the phonon energy. So option A is one of the correct answer. Let us see option B. The ground state of superconductor is higher in energy than the normal state. This is not true. So when the Cooper pairs are formed, the ground state have lower energy as compared to the normal state. So that means option B is not the answer. Option C, in superconducting state, the attractive interaction dominates the repulsive Coulomb interaction. This is also correct because this is only the condition when the Cooper pairs can be formed. If the repulsive interaction is larger, then it won't be possible for two electrons to occupy the energy state of superconducting state. So for to form the superconducting state, this attractive interaction should dominate over the repulsive Coulomb interaction. Okay, option D. There is an energy gap for individual particle excitation, which decreases from about 3.5 kBTC at 0K to 0 at T equal to Tc. So what this statement means is that in superconducting state, there is a energy gap. Yes, if you recall, in superconducting state, there is a superconducting gap. And this gap, it has a value of 2 delta, right? And towards the first part of live session, I said this 2 delta is roughly of value 3.5 kBTs at 0K. So that means in superconducting state for 0 Kelvin, the energy gap is through 3.5 kBTC. And when we increase the temperature, what will happen? If you recall, for T greater than Tc, there is no superconducting state, right? So this gap will decrease. So they will try to move to the normal state. So that is why we say that the delta is maximum and this is 2 delta at T equal to 0K. And when we approach to Tc, then it is 0. Or you can mm, remember one relation that we have seen, 1 minus T by Tc to 1. You can see here delta would be, this is roughly the order. So there is a numerical value which is missing here, which if you multiply by 2 delta, then this will be 3.5 times. And if you see here, if you put T equal to Tc, then delta is 0. Okay. So option D is also correct. So that means A, C, D all are correct. Okay. So is it clear? This question one. Okay. Question 2. Which of this following graph correctly represent the variation of resistivity in a metal and a superconductor? So two graphs for each option. Two graphs are given, one for metal and one for superconductor. So we need to identify which of this option is correct for the variation of resistivity for metal and superconductor. Can you guess which one with the option? Yes, option B. Option B is the correct option. For superconductor, it is dropped to 0 at Tc, but for metal, it is when it drops to 0, there is some residual resistivity because of impurity. Option B. Okay. Question number 3. For T greater than Tc, above the critical temperature, what is the energy required to break a copper pair into two individual electrons? Can you guess? Yes, option A is correct. It is 2 delta. So 2 delta is the binding energy for copper pair. So if you give an energy of 2 delta, then you will be able to break the copper pair. Um, I think, do you have any doubt? I saw you writing some query in the chart section. Okay. So I think question number 4 is somewhat similar to question number 3. What is the energy required to break the super pair, which is 2 delta? It's a repetition. Okay. Let's see question number 5. So you have it's given the critical magnetic field for a superconductor at temperature 4 Kelvin and 8 Kelvin. One is 11 milliamp per meter and other one is 5.5 milliamp per meter respectively. What is the transition temperature of this superconductor? So what you are given the critical magnetic for temperature, let's say T1, which is 4 Kelvin. It's given 11 milliamp per meter. So this unit is for magnetic field intensity. Okay. Please remember the unit also. For B, we have either Tesla or Gauss, but for SC, we have ampere per meter. And it's also given for a different temperature. It's for 8 Kelvin. It is 5.5 milliamp per meter. So what is the transition temperature, which is TC? So let me show you the steps. It's quite easy. You just need to use this equation. SC at temperature T is SC at 0 Kelvin 1 minus T by Tc whole square. So you are given two critical field, these two. So let us take this, let us divide SC T1 with SC T2. So this will be 1 minus T1 by Tc whole square 1 minus T2 by Tc whole square. And if you rearrange this, we need to find out Tc. So Tc will is square root SC T1 SC T2 square minus T1 square SCT1 SCT2 minus 1. We know SCT1 is given 11 milliamp per meter. T1 is 4 Kelvin. SCT2 is 8, not 8, it's 5.5 milliamp per meter. T2 is 8 Kelvin. We just need to put it here. So T says this will be, this value will give 2. T square is 8 square. T1 square is 4 square minus 2 minus 1. This will be roughly 10.6. So the critical temperature, which is transition temperature, is 10.6 Kelvin. Question number 6, it's a conceptual one. A solid superconductor, it's placed in an external magnetic field and it is cooled below its critical temperature. The superconductor, option A, retains its magnetic flux because the surface current supports it, or the superconductor expels out the magnetic flux because it behaves like a paramagnetic material, or option C, it expels out the magnetic flux because it behaves like a antiferromagnetic material, or option D, the superconductor expels out its magnetic flux because the surface current induces a magnetic field in the direction opposite to the magnetic field. So the situation is like we have a superconductor and we cooled it down below the temperature Tc. So temperature is less than Tc. And when and now we are putting this superconductor in a magnetic field. What will happen? Whether the magnetic flux uh, is it retains its magnetic flux because surface current supports it, or it expels out because it's a paramagnetic material, or option D, it expels out because it's a antiferromagnetic, or option D, it expels out because there is a surface current which creates a magnetic field which opposes the magnetic field direction. Okay, so option B is not the right answer. It will expel out the magnetic field, but for the reason for is that the surface current will be created which opposes the direction of magnetic field. In option B, if it was given diamagnetic material, then the option B is also correct. But because it's given paramagnetic, option B is not correct. So option D. Question number 7. So there is a it's given the variation of electrical resistivity with temperature of 3 solid, which is caged on different scale. So we have 3 solid, which is Q, P, and R. And their variation of resistivity with respect to temperature is given. Which one of the following statement describes the variation most appropriately? Option A says P is a superconductor, R is a semiconductor. Option B says Q is for superconductor, P is for conductor. Or option C, Q is for superconductor, R is conductor. Or D, R is superconductor, but P is a conductor. So option A is P is superconductor, but R is semiconductor. B is Q is superconductor, P is a conductor. And C is Q is superconductor, R is conductor, and D is R is superconductor, P is conductor. Option C. Q is for superconductor, R is for conductor. This is what you mean? Yes, Q is all for superconductor, it's correct. But if you look at R, it is resistivity is decreasing. But if we recall for metal, resistivity should increase as a function of temperature. So that means P is a conductor. R is, you can say it is a semiconductor. Because in semiconductor, when we increase the temperature, resistivity decreases. But for metal, which is a conductor, when we increase the temperature, then the resistivity increases. So the correct option is option B. Is this okay? Okay. I think we'll try to solve question 8 and 9. Then I will look at the concept of week 10. Okay, it's given lead is superconducting below 7 Kelvin. So that means Tc is given 7 Kelvin. And it has a critical magnetic field of Sc is given. It is given 800 10 to the minus 4 Tesla. So you can see here it is given in terms of Tesla. That means it is the magnetic field BC. Instead of SC, we have BC here because if you look at the unit of SC, it is of the order of ampere per meter. And unit of B is Tesla and Gauss. So B is given and it's given it is this much for temperature close to 0 K. So let's say it is close to 0 K. And at 2 Kelvin, the critical current that flows through a long lead wire of radius 5 millimeter. So given this information, calculate what is the critical current IC through a lead wire of radius 5 mm. Are you able to solve it? Okay. So let me show you the steps. Yes, I'm showing the formula. So before that, let us see some of the concepts. So similar to the critical temperature and critical magnetic field. So if you have a current I less than IC, then it behaves like a superconducting state. And for current I greater than IC, we'll have a normal state. And if you look at the IV characteristics, then the current is zero, the voltage is zero to critical point, then it increases. This is for superconducting state. SC. So the formula that you should, if you recall, we have seen one formula of current. Let me take this one. So IC for any temperature, let's say we are calculating for 2K or let's say some temperature T. Then this is related to 2 pi A BCT by mu 0. It is the radius of wire and BC it is the critical field for temperature T. Mu 0 is the magnetic permeability, which is value 4 pi into 10 to the minus 7 in SI unit. So that means we need to calculate the magnetic field first because radius is already given mu zero. We know. We just need to calculate the critical field, and which is quite easy because we are given the magnetic field at zero temperature. Then just let's see the relation. So BC for 2 Kelvin is BC for 0 Kelvin 1 minus T by Tc whole square. This is given 800 into 10 to the power minus 4 into 1 minus T is 2 Kelvin and critical temperature is 7 Kelvin. So if you solve it, you will get 800 10 to the minus 4, 45 by 49. So that means IC, okay, it is 2 pi. Radius of wire is 5 mm. So 5 into 10 to the minus 3 and critical magnetic field, which is 800 into 10 to the minus 4. T equal to 2. So T equal to 2, it's already given in the question. So because if you look at the question, we need to calculate the critical current at temperature 2 Kelvin. So that means we need to calculate the critical field for temperature 2 Kelvin. It's already given in the question. Okay, so BC we have calculated. This is this, and we have 4 pi into 10 to the minus 7. So this will roughly give a value of 1837 ampere. And if you look at the options, the closest option that is matching our answer is option D. So answer is option D. So is this question clear? So there are many concepts that you can use to calculate the field and the current. Okay, question number 9. It's conceptual one. It's saying consider the BCS theory of superconductor. Which one of the following statement is incorrect? Option A, presence of energy gap at temperature below the critical temperature. Or option B, differential critical temperature or isotope. Option C, presence of Meissner effect. Option D, quantization of magnetic flux in superconducting ring units of H by E. Okay, so if you look at option A, it says whether the BCS theory tells that there is a energy gap at temperature below the critical temperature, which is correct because for temperature less than Tc, it's a superconducting state and we'll see a gap in energy because of this superconducting gap. So option A is correct. Option B, differential critical temperature or isotope. What does this mean is that for different material, we have different critical temperature, which is also correct. BCS theory does tell about this critical temperature for different isotopes. Option C, presence of Meissner effect, which is also correct. It tells about the Meissner effect. So if you put a semiconductor inside a magnetic field, so it will expel out and magnetic field inside this superconductor is 0. Now, obviously the answer is option D, but let us see whether it is incorrect or not. So option D says quantization of magnetic flux in a superconducting ring in units of H by E, which is not correct. So if you look at the squid, which we have discussed towards the end, I think it's better look. Where was this one? The flux, it is quantized. So if you look at this, phi is n pi. H cut, if you write it as h by 2 pi, so pi will cancel. So it is n h by 2. So it's a quantum number, n is quantum number. So this is the constant. So that means flux is quantized in terms of h by 2a, not h by e, for a superconducting ring. Okay. Mhm. So option D is not correct. Okay, I think let us see. We'll try to solve this question in our next lab session. We only have, I think, 4 questions. Let us see some of the concept from week 10. Okay. So is it okay if I start concept of week 10 off? Or if you want me to solve this, then I will try to solve this. Okay. So let me reiterate. So I will not go in details because we still have next week to go through the concept in details. But just for assignment purpose, I will try to few of the concept from week 10. Okay. Let us see the slides. Okay, I think the slides are visible, right? Okay, so one of the concept is that, so in week 10, we are basically in the first part of this lecture. So we're basically dealing with why we need a charge sensor. Why don't we use a current sensor? So the reason for is that is in this figure. Okay. So let me just give just brief details. So we are studying this diagram. So this is one of the typical uh, charge stability diagram of a quantum dot system, which we have seen earlier. So these are the Coulomb Blockwood region, which is gradually increasing. Then it's not able to see the Coulomb Blockwood in this low current region. So why we need a let me choose different. Why we need a charge sensor? So the reason for is that if we see, let us see when we go from right to left, that is in this direction. So we are moving in this direction. So let us see what is happening. So if we move from right to left, that means we are decreasing the gate voltage, right? And we are decreasing the number of electrons that is there inside this quantum dot. And also this, if you look at this figure, the size of the quantum dot is getting decreased when we move from right to left. Size of quantum dot, it is decreasing when we move from right to left. So this means that if there is a rule that, sorry, there is observation that the number of electron will decrease. Now, can we guess if we move from right to, sorry, right to left, can we guess that in this low current region, can we say that the total charge or total electron is zero? So this is the main discussion. Can we say that this is zero? This is 1, 2, 3, 4, 5, 6, and we found that this is not the case because even though it's a low current region, the charge is not zero. So the main reason we are getting the low current is that if you look at the experiment, for experiment, uh, you you use some detector or some device to calculate this current during the quantum experiment, but experimentally this devices is some limit, so they have limit beyond which they can't measure the current. So because of that, in the low current region, if you look at this diagram, so this is the saturation point, or this is the threshold point of a device. So below this value, the device is not able to measure the current. So that is why it's showing that the current is zero, or the uh, current is low. But it doesn't mean that the charge is also zero there. So for that, how we can say is that why we are saying that the current is zero. So when we move from, let's say, right to left, the current is decreasing gradually. So we are moving from a region of high electrons or a high number of charges to a region of few number of charges. And when we move, the current is decreasing. So for right reason, we have a larger dot. Left reason, we have a smaller dot. And for the right, the current is high, means the source and drain barrier, it is thin. So in picture, what we mean that this source drain barrier is thin. So that means the tunnel rate, because it has a thin barrier, the tunnel rate, which is gamma 1, 2, we have seen earlier, it is high. On the other hand, in the left side, we have a small dot, and the source drain barrier, it is thick. So that means we have a more thick barrier of source and drain. So this is the few electron region, and because of this thick barrier, the tunnel rate is low. So that is why we can say that when we move from the right side to the left side, the current is getting low. It is because of the thick source drain barrier. This thick source and barrier decreases the tunnel rate. That is why we're seeing a low current in the right side. So for this part, due to the low current, due to this low value of gamma, then for this reason, we can't measure the current because the device is getting saturated there. The device is not able to measure what is the amount of current that is flowing because of the low tunnel rate. So for this case, we can't use current as a sensor. So we can't use this parameter I to use it as a sensor. But instead of using current, what we can do, we can use the charge. we can uh, utilize charge, or in right term we can analyze what is the change in conductivity in the IV characteristics. If you analyze this reason where the conductivity is changing in a arbitrary manner, then in that case, it's still possible to measure what is the, it can be used to see what is the number of carriers there. So instead of using current as a sensor, we use the charge as a sensor. So this is why we need a charge sensor, because in the low current region, the tunnel rate is, one is the tunnel rate is very low, and there is thick source and drain barrier. And also the device is not able to measure the current below that limit because it has a threshold. So to overcome that, we need a charge sensor. And there are different types of charge sensor. One of this example is quantum point contact. Okay. So let us see in brief. I mean is that these are completed. Okay. Where is the slide? Oh, I think it's not there. Okay, let me draw it by hand. So you can use quantum point contact as a charge sensor. So if you look at the conductance versus the voltage graph, so you can see that there are they behave like this. There are plateau region and there is a linear region for the variation of conductance. So you can see it here for a very applied small voltage. You can see the conductance is changing by large amount. So that is why we can use the conductance as a parameter to use it as a sensor. Okay. So, and the reason is that in a complete picture, if you look at, this is the conductance variation and this is the current variation. So around this reason, we can use it as a charge sensor, because uh, we'll see in next lecture, next lab session is that if you increase the voltage, you can see that the oscillation in current gradually decreases when we increase the voltage in negative direction. But if you look at the conductance graph, it's not the case. So we have a graph like this. So even though we increase the voltage in negative direction, we still able to quantify this reason. So that is why we can use this around this point, we can use Okay, actually, because it was disconnected from the internet, when I tried to rejoin it, the setting was default, so it was my voice was muted. So I think it's fine for now. Okay. So what I was trying to say is that let us see some of the difference between when we look at the metal semiconductor junction and a superconductor single electron transistor. So in a metal semiconductor junction, if you recall, then the current is it is zero up to the charging energy. Up to the charging energy, the current is zero, and above it, it is non-zero. And when we change the gate voltage or source to drain voltage, then we'll be able to narrow down this region so that we'll see ohmic. This we have seen in the previous section when we try to cover the quantum dot junction. For the superconducting, if you have a superconductor single electron transistor, for that case, because of this superconducting gap, we'll see that the current is zero up to the superconducting band gap. Then after that, the current is non-zero. And we also have one of the curve where the current is non-zero. It is non-zero up to this point here. Then it increases. The blue one, it is for the Cooper pair. And the purple one, it is for the case where we have a quasi-particle state. So what I mean is that for the Cooper pair, if you look at the superconducting energy band diagram, this is 2 delta, right? So one of the if you have a voltage which is correspond the Coulomb, sorry, the Cooper pair can also show the Coulomb Blockade oscillation. Also, these single particle states or quasi-particle state, they can also show the Coulomb Blockade oscillation. But the reason for, sorry, the range of voltage is different. For single particle or quasi-particle is different. For Cooper pair, it's different. And this is what's shown here. And if you calculate, if you recall, for this one, normal metal semiconductor, we can see the Coulomb blockade oscillation if we have a tunnel resistance between source and drain, which is greater than H by E square, which is 25.813 kilo. But for the superconducting state, because of this superconducting back, to see the Coulomb blockade oscillation for this Cooper pair, we need to have the tunnel resistance should be greater than H by 4 is. So this is for the Cooper pair. That is for the superconducting state. But if you look at this quasi-particle state, for this state, the Coulomb blockade oscillation can be observed if the tunnel resistance is greater than H by S, which is 25.83 kilo. Okay. So we have different tunnel resistance for superconductor Cooper pair, also for the quasi-particle set. And if you calculate this value, this will roughly come. It is 1/4 of 25.813. So that means it will give 6.45 kilo. RST. You mean this one? This two. Okay, so one RST I have written for the superconducting state. So when the Cooper pair, when they are involved in the transport, when the transport is because of the Cooper pair. So for that state, we have the tunnel resistance should be greater than a minimum value of 6.45 kilo for the superconducting state. But if you look at the normal quasi-particle state, if these states are involved in the transport, or if you look at the normal metal semiconductor, the RST, it is should be the value that we have seen earlier, which is 25.813. For this state, it should have a value of 25, but for the Cooper pair, it should have a value of 6.45, which is H by 4 is. Okay. I think this is all that I wanted to cover. So let me ask, do you have any other doubt before ending our session? Otherwise, we'll try to wrap up for today. Okay, so we'll end our session for today. So thank you for joining the session. I hope whatever I've covered is helpful to you to solve the assignment or to understand the concept better. Okay, no worry. If you have any doubt, you can ask in the next live session. We'll try to cover more details of week 10 and solve the problems that we haven't solved in week for today. Also, some problems from week 10. Okay, so we'll end for today. Thank you for joining the session. So for now, for today, goodbye everyone.